Alright guys, your boy Chili here, back at you with some more Visual Studio based C++ goodness. It's probably been a while since I recorded something like this, but I figured it was time. Plus, I forgot to turn off the Patreon, so I figured, gotta throw my boys and my girls a bone, if you know what I mean. So, we are creating a project. Well, I said create, and it's now, okay, yeah, it got there. It eventually got there. So, create a console project here, and, well, what are we going to do? Well, we're going to do some multi-threading funsies, as the name of the project implies. So, first things first, we would like all the goodness. We want the new hotness from C++, always and forever. So, we're going to do that, and I think that's all we need for settings. I'm going to get rid of this craft. And I'm going to get rid of this, and it says int main, but then it doesn't return anything. That's dumb, right? Okay. So, getting started. What do we want to do? Well, we want to do some multi-threading. So, we need some work that we can multi-thread. So, let's make up some work. So, how do we do that? Well, I'd like to have a data set. So what is my data set going to look like? I would like a std vector, so I guess I'm going to need to include vector, and I probably want to include array. Yeah, okay. Okay, so I want a vector of std array of int. And how big is our array going to be? We'll call it data set size. Like that. These are our data sets, and we'll do 4 data sets. Okay, so we don't define data set size, so let's go in Const Expert in there, size t. Data set size equal to, and we're going to set this one up as, let's go 5 million. $1 million. Yeah, that looks good to me. Okay, so this is going to be the data that we're working with to start things off. Now, I'd like to, initialize that to some random numbers just for funsies. It's no fun if they're all the same number like they would be possibly if this were, running in debug, where it tends to initialize all your memory to some value. So, random. Okay, now I think a nice fast random engine would be minstd rand. We'll call this our random number engine. Okay, so now let's initialize all of our data sets for each auto array in data sets. Yeah, I just woke up from a nap, so that's why my fingers are, I'm getting my S and my A backwards, you know what I mean. That's what I'm going to blame it on. Yes. Okay, so let's include ranges. Yeah, we're going to get some ranges going on in here. So, std ranges. Let's generate. We're going to go over the entire array, and we're going to use the random number engine to generate values to fill that array. There you go, Bob's your uncle. We have got our data set all set up. Let's see how long that takes to run. This is a fast random number. Yeah, okay. It pretty much ran immediately, I guess. Let me put it in release mode. Actually, I probably want some way of, measuring time. And what I would like to do is just pull in some code that I have You guys may be aware of it. I call it the chili timer. So yeah, we're going to take this chili timer. I'm going to pull that over here. I'm going to pull that into source files. I'm going to remove this because I don't use it. I'm going to remove this because I'm not going to use it. I'm just going to put everything in this filter here. And we're going to include chili timer.h. Okay. So let's do chili timer dot mark auto t is equal to timer dot peak, and let's see, generating the data sets took t second. There. Okay. And we'll just make sure this works. Should be a small number. Generating the data sets took 0.11 seconds. Well, I don't know. Maybe that's how long it takes. Meh. Sure. Whatever. It doesn't matter to me. All right. So we have our data sets. Now, what we want to do is we want to do some serious work on this data. All right, so I got an idea here. I'm going to include CMath, and I'm going to include limits. So what we're going to do is, we have the full range of int values, which I guess is like around negative to positive 2 billion. I want to do some math on it. I want to do some expensive math, which typically means floating point math. So, for each auto array, and we'll call this one set in data sets. So we loop all through each set, and then for each auto, let's do int x in set. Yeah, that seems good to me. What do I want to do? Well, I want to do some trigonometry. Trigonometry is typically run on, values that are between positive and negative 1, if it's like a sine or a cos deal. Am I getting that right? Yeah, that's how that works. So let's do const expert auto limit is equal to double std numeric limits of int. We'll get the maximum value of an int. Get that at compile time, by the way. And what we're going to do is we're going to do const auto y is equal to double x divided by limit. So we'll scale x by its maximum value, and that should bring it into the range of right about, negative to positive 1. Then we're going to do some work, and we want to accumulate that work in some place, but I don't want to create another set of variables to store it in. So I'm just going to store the work in the first element of the array. So array, we'll do set at 0. We're going to plus and equals that with integer std sine std cos of y. So this will do the sine of the cos, which I don't know, is that... Okay, yeah, I was getting a little mixed up. Like the argument of sine and cos is typically not in the range of 0 to, negative to positive 1. It's in the range of, negative to positive pi or whatever, pi over 2 or whatever you like. It doesn't matter. What we want to do is convert whatever we get out of this, which will be in the range of, absolute value of 1. Convert that back to the full range of values for an integer, and then convert that to an actual integer and then add that back in. So what we're doing here absolutely does not matter at all. It's just some work, and I want the work to require a fair amount of CPU power, because if the jobs aren't CPU limited, then we're not going to see much of a benefit in multi-threading them. So we've got our data sets here. Put that there. Let's put that there. And processing the data sets took, how long is this going to take? Well, let's take a look. How long do you take? About 0.4 seconds. 410 milliseconds. Okay. So that's a fairly beefy amount of processing. And let me just say before we move on, definitely loving ranges here. I mean, I love being able to just type the name of the container, and that's it. When you're good to go, you don't have to type, r.begin, r.end. It's just one bad boy and you're good to go. I love that. I'm loving the ranges. Second thing, you might wonder, well, if you're going to make this an array, and you know that you're only going to want 4 of them, that's fixed at compile time, why aren't you making this one an array, Chili? And that's a question I'll leave it to you. Why am I not making this an array? What would happen if I made this an array? You can put your predictions in the comments down below. But anyways, so now what we want to do is we want to multi-thread this. So first off, yeah, we're going to include thread, obviously. Now, to multi-thread stuff, to launch a thread, it's very simple in C++11. You create a thread object. When you're creating it, you pass it a function or some kind of callable thing, and then that function that you passed will be executed on a different thread. Well, yes, it'll be executed on a different thread. It's not guaranteed that it'll be executed on a different core. Parallel, like if you only got a CPU with one core, obviously it's not going to run in parallel with the code that you're already running, but you're going to get another thread. So, we need to create thread objects, and we would like to store them somewhere because they are useful for one main reason, which we'll get into. So let's create another std vector, and we'll make that of std thread. Yeah. And we'll call this one the workers, because those are going to be our worker threads. Now, we want to do this. We want to do this work inside of threads. So let's try it out here. We're going to go auto w for worker is equal to, now our worker is going to need access to the set. So we're going to give it the set as a reference. Now I believe in C++ 20 you can actually maybe omit the round boys if you're not using them. So we'll do that, and then we'll cut this out and put that in here. And then we need to, yeah. Man, I think we're done. So that's that. And then we're gonna go workers.pushback. We're gonna create a new std thread, and we're gonna pass it the worker. And that's what's gonna be launched on a new thread that we create. And there you go. Bob is your uncle. Let's put in debug. There's no reason in particular. I just feel like putting it in debug. And let's run it. It compiles, and we get a big debug error. Abort has been called. Well, that's not good. That's usually not good, right? It also only took 0.001 seconds to process the data sets, which is 400 times faster. Amazing. Very amazing, considering what? How many threads did we launch? Well, this is a loop. It's looping over the data sets. There are 4 data sets, so therefore we launched 4 threads. We launched 4 threads, we got 400 times faster performance. And you're thinking, Chili, wow, this multi-threading is better than I expected. No, of course not. So, the object thread, the class, has a destructor. And basically the way it works is if you call the destructor on a thread and that thread is still running, it just tells your program to crap the bed, because that's not supposed to happen. You're not supposed to try to close your program while you got your thread still running. So what do? Well, you wait for your threads to finish, then you exit. And that makes sense for a number of reasons. First of all, if we don't wait for our threads to finish and we call timer that peak, we haven't actually finished processing the data sets. We just started the jobs and then said, okay, done. I'm done. Now you gotta watch your workers. You gotta make sure they finish their goddamn jobs. So what do? Do we install spyware on their laptops? No. We join. Don't ask me why it's called join. It's dumb. But it is called join. So what you do is after you've launched your 4 threads, then we're going to loop over all of our workers, and we're going to say, okay. So for each one of these ones, wait until he's done. So we're going to do w.join. And that's going to wait until that thread is done. So we're going to wait until the first thread is done. And when that one's done, then we're going to make sure that the second, the third, and the fourth are also done. And if any of them are taking a little bit longer, then we'll wait for them too. And when we finish this loop, that means all the threads will have been done. We checked all 4 threads. They were all done. So now let's mark that we're done our processing. And then let's exit. Let's GTFO. And there you go. Processing the data sets took 0.18 seconds. Well, okay. Well, I mean, if you're in debug, things are going to run slower than you expect. So let's put it in release. Yeah, 0.11 seconds. So first time we ran it with a single thread, took around 400 milliseconds. Second time we run it, 4 threads, about 100 milliseconds. 4 times the threads, about 4 times as fast, which is kind of what you would expect. And there you have it. That is the beauty of multithreading. We've done it. We have finished. We've learned all we have to learn about multithreading. Go out there and build the next super scalable Minecraft. You have my blessing. Not really, but for this video, I think we did a good thing, I mean, I think to me, I can't remember that far back, but I imagine to me it seemed a little bit like dark magic. Like, how do you even run your program in like multiple, it's running in parallel on the same time in space, and man, that's crazy. And then you learn how to do it and you say, well, that's actually really goddamn easy. What's everyone complaining about multi-threading? It's so easy. Why doesn't everybody do it? And then you'll learn about synchronization, inter-process communication, and they say, oh, that's why people don't try to multi-thread absolutely everything, because it's a big pain in the ass. So, and we'll get into that, eventually. But today, now we're just gonna look at the fun stuff. So, one more thing before I wrap this video up. You see here, I create a lambda here, and then I use that to puts that thread in, and I like lambdas. It's nice to put your implementation at the same place here, but let's try it a different way without a lambda, okay? Just for funsies, and then we'll see something interesting there as well. So I'm gonna make a function void process dataset, and we'll make it take in data as a state array, right? Because with this one, we could bind the lambda, but we don't, for just a normal function, there's no binding. So you got to take in the stuff as a parameter. So int dataset size, and we're going to make an ampersand there. Not making it a const reference because why? Because we're assigning back to that array, so that wouldn't make any goddamn sense, would it? Of course not, Chili. Of course not. Nobody said it would. Then we're going to copy and paste that into there, and we'll call this set. And we're good to go. So now what are we going to do? Well, instead of launching this with our lambda, why don't we just launch it with our process dataset? Here. Nothing could possibly go wrong. Right? Everyone's 100% behind me on this one. Oh no. No, we've got template compiler errors. Well, I guess I'll just die. That's what a lot of people say when they see compiler errors for templates. They say, I guess I'll just die. I'm not reading this. No matching overloaded function found. No matching overloaded function found. Well, why is that? See reference to function instantiation being compiled. Thread std array reference. So there's a little bit of a hint in here. Fail to specialize template. See declaration of std invoke. Yeah, I mean, this is mostly just garbage. These diagnostics are garbage. I hate them. But luckily, I already know what the problem is, right? I mean, it kind of says it here a little bit. So the function that we're trying to pass this thread takes a parameter, but we're not telling it what the parameter. We're not giving it the parameter to launch this function with. So things don't match up, and then the template compile template metaprogramming is like, you're missing some shit here, boy. So what are we missing? Well, we got to pass in the set. We pass it in as a reference, of course. So we'll just do that, and of course this will work now, won't it? No, of course it won't. What were you expecting? What are you, bright-eyed, bushy-tailed, thinking everything's gonna work? Things don't work. This is C++. So what's the problem? Well, I mean, this one is going to probably be even harder to figure out unless you know what you're doing ahead of time. So that's why I'm here. That's why you're watching this video. You're getting some experience. If you could just learn it all by looking at CPP reference, then you wouldn't need me, would you? Okay. So basically, because of the way that the machinery of the std thread and everything works, and you know how references do be like, you can't just pass it a reference. One does not simply pass a reference to this thing that gets stored somewhere and then gets passed on to the function later on. One does not simply do that. So what does one simply do? Well, you wrap it up in a reference wrapper. So you call this function stdref, and that creates a reference wrapper around your thing, and that allows you to package up your references so that they can be transported across the dimensions to your thread. And that's how it works. If you want to pass references to your function for thread, you got to wrap that shit. You got to wrap it. Don't double wrap it, just single wrap it. Chili always says, one wrapping is sufficient. And then if we do this, then it works. And then if we run it, yeah, it works the same. It's the same thing. It's the same thing, it's different pile. You have a separate function, you have a lambda function, you have a bind, you have a parameter, whatever. You do you, is what I'm trying to say. You do you. But here you go. Here you have it. Launching our threads, joining our threads, and getting 4 times the performance and love and life. But that's where I'm going to put this video. That's where I'm going to hit the stop button. And then the video will end. And you'll get another video, but it won't be this video. You know what I mean? YouTube, to be serving up the videos. I don't know what I'm talking about anymore. But anyways, yeah, I'm going to make more videos on multi-threading if you guys like this stuff. And if you don't like this stuff, then I'm not going to do that. I'm going to do something else, and it'll probably involve copious amounts of alcohol. But anyways, in the next video, if there is a next video, I plan to just kind of like take a step back, take a bird's eye view of all the different kinds of multi-threading that we will tend to run into. And, what are their features? What are their modus operandi? What makes them tick? And hopefully that'll give us a little bit of a conceptual framework in which we can approach the topic of multi-threading. But until then, thanks for watching. Hope you enjoyed the video. Click the like button, and I'll see you later with some more C++.